Hi there, and welcome to another episode of Mr. Carlson's Lab. Today we're going to troubleshoot, repair, and modify a signal tracer from way back when. Signal tracers are great tools to have on the bench, and in many cases they can even replace an oscilloscope in many troubleshooting procedures. Oscilloscopes allow you to see what's going on inside the circuitry. Signal tracers allow you to hear what's going on inside the circuitry. So it's just another device on the bench to bring you closer to success in your next repair or restoration. Now, signal tracers like what I'm going to show you today can be had for really cheap at local auctions or swap meets. And usually, because of their age, they're in some state of disrepair. So after some quick repairs, usually they're ready to go. Now, in this video, we're going to go a little bit further than that. The line cord is cut off this thing, and the case is looking pretty bad, so chances are I'm going to do a pretty extensive repair on this. And as we encounter problems inside this, we're going to repair them, and if the design needs any modification, we're going to modify it as well, and I'll explain exactly my thought process as I'm going through these modifications and repairs. So hopefully these modifications and repairs will pass on some information to you to help you in your next repair or restoration. So we have a lot of territory to cover in this video, and I'm going to share some hints and tips with you about vacuum tubes and some other things along the way through the video. So there's a lot of really neat stuff coming in this video. So let's get started. Here you are, sitting right beside me at the test bench, so let's take a look at what we're up against today. This is a Stark signal tracer, and it looks to be in pretty nice condition. There is a probe that's missing on the coax. You can see the exposed center conductor here. Aside from maybe the paint that's been ruined by somebody using a permanent marker and a few screws that are missing, it looks to be pretty nice. Now, one word of advice, if you're ever going to try and sell something like this at a swap meet or online or anything like that, don't write the price onto the paint with a permanent marker, because when they say permanent, they mean it. It does not come off. It goes directly into the paint. Somebody has taken the time to try and take the price off of here. It looks like they've polished it, or they've done something, maybe used acetone or lacquer thinner. And what that's done is that's taken the texture right off of the paint itself. So we have kind of like a flat look over here, and you can still see the price on the paint. That's permanent. That will never come off. You'll have to strip the paint to get that off. And this is what I'm going to end up doing with this. This is not going to be a shelf queen. This is going to be a piece of test equipment that we are going to actively use together to troubleshoot other pieces of test equipment, radios, transmitters, whatever we're going to be troubleshooting at the time on the bench. So no shelf queens. This is going to be an active piece of test gear, and I want it to fit into the theme of the old-time workbench. So what I'm going to do is get rid of this ugly beige color, and I'm going to most likely paint this like a hammer tone black or something like that. That would fit really nice into that old-time workbench. So you'll notice a lot of older pieces of test gear have this somewhat a beigey, nicotine-y type colored paint on it. And the reason that they did that way back when is because it was really quite common to smoke in the lab. Everybody was smoking way back in the day. So by using a beige colored paint on the case like this, when they did get stained, it kind of just blended in and there was a lot less cleaning. Hewlett-Packard used a color that was very close to this, very close to what the Stark has used here on its case as well. So it really is an ugly color, so I'm kind of looking forward to getting rid of this. And the black hammer tone will work better with this white colored face and the black knobs and everything like that, so it'll kind of be in line with everything else here. Probably end up painting this grill here by the speaker as well, because this is the same color as this paint. Other than that, it's looking pretty good. So I don't know what's inside this. There could be a brick sitting inside this thing. As I mentioned in all the other videos, as we go through this and repair this, I'm discovering the problems the same time you're seeing them, so we're repairing this in real time. Now, there is hardly any screws in the case. There's one screw back here, there's one missing here, and the line cord is trimmed off the back side as well. So it's obviously in some state of disrepair. Maybe they trimmed the line cord off for a reason. Who really knows? So what I'll do is I'll turn this thing around. We'll take a look at the back side. And then what I'm going to do is remove this from the case. And we'll take a look at the circuitry inside. Take a look at the design that Stark put together. And talk about that a little bit. Here's the back side of the unit, and as you can see, it's in pretty nice condition. You can see a screw missing here, and there's also a screw missing on the side here and on this side. So it really looks like the only screws holding this together are these three right here. Nice little sticker here. It says Special Inspection Series T approved by the Hydroelectric Power Commission of Ontario. Line cord has been trimmed back here. So why it's been trimmed, we'll find out here very soon. So other than that, it's pretty much ready to be taken apart. So let's do that right now. Take these three screws out and see what happens. They are pretty loose, I can tell you that. That sure is loose. Wow. Ready to fall in. Wow, look at that inside. That sure is clean. Let's move that out of the way. Get a little bit better light on the inside there. Yeah, it's really nice and clean in there. Looks like it may have, I don't know if I can get the light on that. You can see that from this angle here. No. What I'm going to do is I'll just take this out of the case now. So it looks like this is just going to come right out like that. So I'll just leave this here like so, just for a second. We'll take a look at this, and then what I'll do is I'll just get this off the bench. I kind of have to work around the camera here. So it looks like everything in here is intact. Look at how clean that is. Just dust on the chassis. Looks like a brand new unit. I really wonder how much time is on this thing. So what I'll do is I'll pull this out of the case and get the actual case out of the way, and I'll move the camera around, and we'll take a better look at this. Let's take a look at the design of this Stark ST2 and see what we can learn from what they've done. Now, I can tell you this already. I already see a bunch of flaws on the upper portion of this chassis. Design flaws, really basic stuff too. So if you want to guess at what the design flaws are, what I'm going to do is move the chassis around slowly, and then when I'm done moving the chassis around, you can pause the video and take a guess at what you think the problems are, and then when you unpause the video, I'll tell you what they are, and we'll do the same thing for the bottom portion of the chassis. So you want to get your arrow ready to pause the video. So here we go. I'll move the chassis around, and you can take a guess at some of the design issues. So you're going to want to get ready to pause the video now if you want to take a guess at what the issues are on the upper portion of the chassis. These are the issues with the upper portion of the chassis in the Stark ST2 signal tracer. So the first thing that tells me that this thing is going to hum all the time. So if I was to pull the tubes out and everything and just plug the unit in, this thing is going to hum. Why is that? Well, if we look at the audio transformer, look at how close this audio transformer is to the power transformer, and they are both situated the same way. These two are going to couple. The magnetic field from this power transformer is going to couple into that audio transformer, and it's just going to make this speaker hum all the time. This is really basic stuff, and I don't know why Stark did that. This transformer should be out of the way of this transformer, and it should be mounted 90 degrees. So to stop that humming, or to at least bring it down to a very minimal level. The more you'll load the B+ or the filament winding on this, of course that field is going to get stronger, and what it's going to do is create more hum in that transformer. The field is going to interfere with this transformer, and it's going to impose hum into the speaker. So really the only way to get rid of that hum at all in this design is going to be to shut this off. Now you're saying, well, how do you know this? Like, this got some shielding on it and everything like that. Well, when you work with audio design for a long period of time, you get to know that, yeah, they put the shielding on this transformer to probably minimize that effect due to a bad design. Costs a lot of money to put these caps on transformers, so this looks like a patch. So they probably stamped the chassis, put the whole thing together, figured it was going to work, and then realized, oh, there's an incredible amount of hum, so they had to order transformers with caps or get caps put on them. It's the reason they've done this. No matter how much capping you put on a transformer like this, when this transformer is open like this and pretty much almost touching it, like look at the clearance there, you know, very, very small amount of clearance. Right there, you know it's just going to hum and couple. So we're going to try this out here in just a little bit, and we'll slowly go through this thing and repair this together and bring it back to life and see if we can minimize that at all. Really, the only way to fix this design is to take this transformer and to move it somewhere else on the chassis in order to get rid of that just basically, I guess you could call it just static hum. It's just going to sit there and hum for no reason. Now, another problem on the upper portion of the chassis is the placement of this audio power tube. Again, we're in the area of the field of this transformer, and it's a, you know, I can basically just stick a finger through there. So what this is telling me now is that the grid, the control grid of this tube might pick up that stray magnetic field, and the audio output tube alone may introduce hum into this circuit. So what we're going to do is we're going to pull this audio tube out, and we'll see if that, you know, reduces any of the hum at all, and we'll put the audio tube back in and, you know, see the differences. I can tell you already that this is just way too close. This needs to be over here. This can be closer to the front. So you can see this is up here, but there's a lot of room underneath. So this could be closer to the front. That's how it should have been. It gets the amplification chain closer to the cable where it's coming in and to the VR. There's no need for it to be this far back. So the closer you get to the front, the tighter things are. And then they could have taken this tube and placed it somewhere else in here. Maybe you move this transformer over to this area. It would have been the better idea. They could shove all this kind of stuff over. You know, it's just, it's silly. This could have been put right here. Keep the power supply on the other side of the chassis, away from, you know, the whole amplification chain. So there are a whole bunch of design errors in this thing. We're still going to restore the thing and, you know, see how useful we can make this little signal tracer. But if you wanted to take one of these things and completely make it quiet, honestly, what I would do is put an umbilical cord on the back of this thing and put the power supply in a separate box. That would alleviate all the problems in this design. So just get this thing out of here, because it's too close to everything. Like, look at it, it's even this close to the speaker itself. You know, so like, I mean, that field, this whole thing is right within the field here. And, you know, we have a coil inside here as well. There's just so many things. You look at the top side and you see these problems just everywhere. So this tells me that either a young designer put this thing together at Stark, or somebody was just in a rush and really didn't care. It's hard to say. But, you know, the amount of flaws in this design are really kind of over the top. It looks really nice. I have to admit it. Like the way they've laid it out and everything, it looks nice. Nice and compact and everything. But looking nice and working properly are two incredibly different things in the electronics world. So let's take a look at the bottom portion of the chassis now and see what we could do to make that a little bit better and spot some of the problems there as well. Here's the bottom portion of the chassis, and let's take a look around on the bottom portion and see what we can spot. So again, you can take a look at this just like this, and you can get ready to pause the video. I'll move this around just a little bit, and then you can take a guess at what some of the issues are on the bottom side. So I'll let you know when to pause the video here. So I'll take a look at it now. Just a quick little glance at it the way it is this way here. And I'll grab this, bring it a little bit closer, and I'll start moving it around. Again, you can pause this at any time if you want to study something a little bit closer. I think that's just about all angles there. So I'll put this back down. If If you want to pause the video and take a guess at some of the issues on the bottom side, do that now. Here are some of the issues on the bottom portion of the chassis of this Stark ST2 signal tracer. So the very first thing that caught my attention was these two connections right here. If you take a look at those connections, you can see that there's absolutely no solder on them. So the wires have been wrapped, but the connections have not been soldered whatsoever. Now keep in mind that this thing went through a special inspection. Remember that little sticker on the back side of the unit? That's a very interesting special inspection. So if there was any current demand on this outlet, this would be very, very noisy. These would turn into a very, very noisy connection. So that definitely has to be fixed. The next thing I noticed is they're using half-wave rectification. So we can see we have the two red leads, which are the B+ leads. One runs right to the chassis. One goes through the diode, right? So we get DC at this point here. And then there's no filter here. They run it through a 220 ohm resistor, most likely to drop the voltage, and then that runs into this capacitor right here. So there's 3 filter caps in this can. I've yet to discover where they go and what they do. In fact, I'll look for a schematic, and when I find a schematic, we'll take a look at that as well. So they should have a filter here alone that's going to make some more hum. So we'll experiment with this design here in a little bit and see what adding some filters and stuff does to this thing. All right, so we'll go through this piece by piece and try and improve their design to a point. Really, what should be done is, everything should be moved around and the thing should be completely redesigned. But at that point, it's really not a Stark ST2 anymore. Then it's more like a Carlson ST2. So I don't want to change it that much, but we'll make the design, a little bit more usable. Another big problem, ceramic disc capacitors in a high gain audio stage is not a good idea because ceramic disc capacitors are microphonic. You can tap ceramic disc capacitors and you'll hear the tapping quite clearly in the speaker or whatever you're using to monitor what's going on. So these should be some type of a poly. Well, back in the day, they would have most likely had paper and foil style capacitors, but it should have been a poly style capacitor or paper and foil or whatever, way back when to slow down on that microphonic issue a little bit. Sometimes these things are so microphonic that they actually hear the speaker and they start a feedback loop. So they start howling and whistling. So here's the thing with ceramic capacitors. They're great for RF bypass, just general bypass capacitors. These things very rarely fail. So whenever you see these things in whatever you're restoring, if you see these ceramic caps, again, very, very dependable capacitors. They can be left alone most of the time, just like mica capacitors. So that's one nice thing about it is that, that doesn't really need to be recapped at that point, unless, of course, I wanted to change these all out. So one nice thing about ceramic capacitors, that's what they have over the old paper and foil style capacitors. But again, microphonic and an audio chain. So some of the cheaper, older style amplifiers with engineers, again, that didn't know what they were doing, would put these in the signal chain of some nicer push-pull style audio amplifiers. And I just look in there and just shake my head. I did a video on how microphonic these things were. I actually tapped them and you can see it on the scope just by tapping it. And there's some pretty large spikes just by tapping the ceramic capacitor. So what I'll do is I will link that video below. So just below the video is a description, and below that description, you'll see show more written in capitals. If you click on that show more, it'll expose some links underneath there. And if you click on that video, you can also go and watch that. You can see how microphonic these caps are. I've had lots of people that are skeptical about that. They're like, oh, they're absolutely fine in an audio chain. No, they're not. So those are just some of the issues on the bottom side. Again, tube placement and everything. I could keep going and going. For my own use, I don't want just a cable running out to a single probe. What I really want on the bottom side is a BNC style connector so I can put whatever probe on the front I want. And if I also want to, say test a noisy resistor of some sort, I don't need to be fiddling around with a probe with a little bit of a tip on the front and an alligator clip or something like that. I can clip the resistor in, put it off to the side so I don't have to hold anything, because this thing routes high voltage out of this probe lead right here so you can test for noisy components, and I'll show you that here in a little bit as well. So I want a BNC connector on the front here, something that I can either put a probe on, I can put an RF probe on, I can just put a pair of alligator clips on a piece of shielded cable, something like that. So this is really what I want. So I'm going to install a BNC here. It's just a much better option. Something I definitely need to do because everything I have has got, BNC connectors on it, right? Line cord could get fixed up here. Of course, we can see just a line cord coming right in and nothing happening there, so that needs to be fixed. It was cut right off. Why, I don't know. We'll find that out here in just a little bit. So that is just some of the problems on the bottom side here, and as we're testing this, we may find more. Some things maybe open resistor, something like that. Who knows, right? We'll just go through this and take our time, find out exactly where the issues are, and try and solve what we can in this design. The design is most likely going to be salvageable, but it's going to have some problems that are just going to hang around, I'm sure. So let's get into that. I may also actually, just before that too, is remove this and maybe get some black paint on this nice little grill right here, because I've already got the cabinet off and I'm ready to repaint that cabinet, and I kind of don't want to leave this ugly beige color, so I'll probably coat that black or silver or something like that. I'll figure that out in a little bit. So I'll remove the 4 screws and take this off. It's just pinched between the speaker and the face of the unit here. So I'll get that underway as well. I got the grill out of the unit right here, so it looks like somebody had even drilled the grill wrong at one point. So these are the 3 holes here, and then this one here is kind of elongated. It was in here like this. So to get the grill out was really quite easy. All I had to do was just remove the 4 screws on the face and just slide the grill out. And the speaker itself is in very nice condition. So what I'll do now is I'll put the screws back in just to hold the speaker in place and be very careful that I don't poke at it. And I'll repaint this grill a nicer color. I'm still kind of undecided, something that'll work well with the face. I'm ready to start glass bead blasting the case right now. So right now it's inside of a big blasting cabinet, and the noise that you hear in the background is a vacuum with a big filter in it. What it does is it draws air through this case and then of course filters that air out. When you're glass bead blasting in a case, it tends to get really dusty in here, so it draws all of that into a canister with a big filter in it and filters it out. So it draws air on the back side of the cabinet. So what I'll do is I'll just put my mask on here first. I'll get a little bit muffly sounding. And then what I'm going to do is grab the glass blaster and I'll start taking some paint off, and I'll show you how that works. So here we go. I've got my mask on. Okay, let's see. I'll start right about here. So you can see how quickly it takes that down to bare steel. That's just raw steel right there. So the process is really, really fast. It'll clean this right down, and it's pretty much ready to paint directly after that with that hammer tone style paint. It leaves a nice surface on top of the unit itself so that the paint really sticks well. Before I paint it though, I'll use some brake cleaner, things like that, to clean the steel off to make sure that there's no wax or oils on it, because I don't want any problems with the paint sticking to the metal. And it is in this large cabinet here. So that's the glass blaster. So I'll keep on going and get the entire unit all blasted and painted. That should make a really nice looking cabinet. I'm looking forward to seeing what this looks like when it's all painted up. In order to start the troubleshooting procedure on this little signal tracer, the first thing that I'm going to do is get some of the basic stuff out of the way first. So I'll solder up these terminals here. I'll have to put something underneath here to press this wire away because it's actually touching this terminal here while I solder it, or it'll melt into these wires here. So I'll get these 2 terminals soldered up. That was obviously forgotten during the assembly procedure. And then what I'm going to do is cut out the remainder of this line cord and get rid of this little well, this is a restraint, a cord restraint on the back side here. I'll get rid of that during the testing procedure. I'm just going to put a cord in here temporarily while we're doing this. Reason being is the hole in the back panel that fits on this unit is not large enough to fit a plug through it. So I actually have to put the panel onto the back side here and then put the cord through both. So I'll show you the little hole in the back panel here again in just a little bit. So the plug is pretty wide and of course the hole is pretty small. So just for testing, I'll get rid of all of this stuff here and feed a line cord in, and we'll begin the procedure at that point. I had to remove the wattmeter socket from the front of the unit so I could clean up these incredibly oxidized contacts. They would not take solder at all. So I could apply RA flux, feed solder in, it would just ball up and roll off. So after a little bit of time working with this in the chassis, trying to make it accept solder, I just said, that's it, I'm taking this thing out. So I ended up cleaning these things up really well, applying RA flux again, and then working solder onto the surface. So these are pre-tinned, so when I put this thing back in now, it'll very easily accept solder. These were very, very stubborn. So that's fixed up. I'll reinstall this, probably put some new screws in the front while I'm at it, and I'll get to the line cord. I've temporarily installed a line cord into the signal tracer. This line cord runs off to my current limited isolation transformer in variac supply. That supply is going to allow me to safely bring up the line voltage slowly. Now, if there are any issues in this unit, any major issues, that current limited supply is going to take care of that, and I'm not going to cause any further damage to this little signal tracer. If you recall, they did cut the line cord off on the back, so there might be something majorly wrong with that power transformer. Again, we'll discover all of these issues together. What I want to do is I want to bring you through the entire troubleshooting and repair process. So when we discover a problem, we're going to take a look at that problem and see how that problem affects the rest of the circuitry. That is absolutely crucial in troubleshooting, not only just repairing the unit, but actually understanding why the unit is acting the way it is in its failure point. Again, very, very crucial in troubleshooting. So we're going to do that together. Now, if you're following along, you're doing so at your own risk. Know that there is high voltage present all over vacuum tube gear, and in this unit there's AC line open, basically just right here like this and up here. In these older pieces of gear, they didn't take the time to put heat shrink tubing over everything and make sure everything is majorly safe. They just expected you to know that this is dangerous, and this is very dangerous. So all vacuum tube equipment has high voltage present all over the place, aside from space charge circuits, and I'll talk about them in another video. But most vacuum tube gear has high voltage, and some of it's got extremely high voltage present. And of course we have, the AC line present, which is high voltage and high current there as well. So if you're unfamiliar with working on a unit like this, let me do the dangerous stuff. Stay away from a unit like this until you're familiar with the circuits, until you're comfortable with that circuit. If you are not comfortable with working on circuits like this, don't work on them. Don't put yourself at risk. There are lethal voltages and lethal currents available in this chassis. So again, if you're following along, you're doing so at your own risk. Be very, very careful. I'm ready to apply AC to this. Let's see what happens. So, turn on the supply, and I'll slowly bring it up. I can already hear the speaker humming. That would be that coupling issue, I'm pretty sure. Well, there's definitely a hum there. Now, the dim bulbs, or the bulbs on the current limiting supply, were on very, very dim. So there wasn't really any excessive current draw there. So it's just making a really bad racket. So let's look into why it's making that racket. So far, we know that this very small signal tracer has a very big hum, and we need to figure out where that hum is originating. Now, in an audio amplifier circuit, hum can be caused from a whole bunch of different things, and that's really what this thing is. It's just a very sensitive audio amplifier with a really high gain stage in the front end. So the hum could be originating from the signal path, it could be heater to cathode leakage in one of the tubes or both of the tubes, or it could be main power supply hum, so the main B+ supply might have ripple on it. Now, the very first thing that you always want to check is the power supply, and what really points me towards the power supply in this little unit is that the hum is so incredibly strong. It's incredibly loud on this end. So that tells me right there that I should be checking the power supply first. Now here's something to always keep in mind whenever you're working on an audio amplifier. In this case, this is the B+ supply, and we're supposed to have nice, clean, filtered DC at this point. That's what this capacitor is here for. It's to take the ripple off of the DC so that we have nice, clean DC. Here's the thing with high-gain audio stages, and this applies to phono stages and any type of audio gain stage. If there's any ripple or AC present on the power supply, since the power supply is powering up the amplifier stage, what it's going to do is it's going to take that ripple that's present and insert it into the amplifier stage, and what it's going to do is get amplified all the way down the line as you get closer to the output. So basically it's taking the noise from the power supply and amplifying it and making it worse as it gets further and further down. So the more gain stages you have, the more it's going to take that ripple that's kind of leaking into or mixing into the amplification chain. It's going to take that and make it really, really bad. So it's very important in very high gain stages and just amplifiers in general to have a very, very clean DC supply. Now that's another thing that brings me to the design of this thing. I look at this and I see, okay, 2 red leads coming out of the transformer. So immediately when you see a transformer with green and red leads, so green, red, and black, we know green is the filament leads, red is the B+ leads, and black is the main AC line. Sometimes it's black and white. At any rate, I just did a video on Patreon explaining how to recognize leads on transformers. So if you're interested in that, you're going to want to go to Patreon and check that out. It's an entire video based upon that, and also determining transformer impedance as well. There's some equations up there, a math equation and stuff to help you figure out how to determine the impedance of audio transformers, unknown audio transformers. But at any rate, back to this. So we know that we can see these 2 red leads. These are the B+ leads. One of the red leads just ties directly to the chassis, and we see the other red lead going right into this diode. So one diode. That means that we have half-wave rectification. So half-wave rectification going through a resistor and then directly into a filter can. And if I look at the filter can, there's hardly any, it's hardly any filtering there, 50 microfarad or something like that. I'm just looking at this just going, what is going on with this design? At any rate, it just keeps getting more interesting as we go. But let's fix one problem at a time here. So let's see how much ripple is going to be present at this point, if there even is any. Maybe they have done something right. So let's take a look at this point, and if there is ripple here, right there, we know that this capacitor is most likely going to be at fault, and we'll test that cap. So let's do that right now. So I'll take the black lead of my meter, since we're going to be looking at AC, this could be classified as a common lead, and I'll take the red lead and put it right here onto the B+. So this is right where it comes out of the diode, and it's right to the very first filter capacitor. I'll turn this on to AC, and I'll turn on the backlight like so. Now what I'm going to do is turn on my variac and isolation transformer, which is going to give this AC line voltage. And I'm not going to leave this on for too long because I imagine, the hum is so incredibly intense on this end. It's probably really hard on that small audio transformer. So what I'll do is I'll turn on the supply now. I can hear it in the speaker. I'll click the speaker off in a second when it starts to hum. So my finger's on the switch here. Wow, that's loud. Look at the amount of AC there. That's supposed to be clean DC. There's almost 9 volts. There is 9 volts. 9 volts AC. And take a look at the ripple here. 9 volts AC at that point. So I'm going to shut this off. So there's only supposed to be DC present right here. and there's AC on there. So to give you an example here, what I'll do is I'll just click this over here to DC. So we can tell that we do have some form of filtering there because there's DC that's lingering at this point. So we do have some form of filter capacitor happening over here. You can see how it's climbing. So there is something working there. So we do have some form of capacitance in this capacitor. So it'll be very interesting to try this. Why do we have so much AC at that point? Look at it's climbing. It's not even on. This is one of the dangers with capacitors. So, and this is called dielectric absorption. The capacitor, there's nothing applied to this right now, like the power supply's off, there's no AC applied to this, and as you can see, that's just climbing up. So, this is the kind of stuff that gives technician shocks, and this is why it's so incredibly important to safely discharge capacitors, because that can keep climbing and climbing and climbing. And in some of their very large capacitors, that'll climb up to 100 volts. Sometimes even 200 volts, it'll go right back up there again after sitting for a long period of time. So really, really dangerous. So you can see this is starting to settle off and go the opposite way now. So what I'm going to do now is I'm going to turn the AC supply back on. Now this is the same point where there was AC, and as you can see there's DC there as well. And we have about 130 volts DC there. And if I click on the speaker again, you can hear how incredibly loud that is. So it's probably pretty hard on that audio transformer. So we have a lot of ripple present at this point right here, and we need to figure out why there is ripple there. So what we're going to do is check these capacitors. What I'll do is I'll desolder the leads off of these capacitors here, and we'll verify this and see how close they are to the actual spec. I've desoldered all the leads from the 3 capacitors in this one can so we can test each section individually. So all 3 of these capacitors have one common ground, which is attached to the can, and the can is soldered to the chassis. So we can just take the negative lead of the capacitor tester and attach it to the chassis and just test each capacitor here. So I'll just turn on the capacitor tester right now. Now there should be 2 50 microfarad sections and one 20 microfarad section. So let's see what we get here. Well, one section has half, or just under half, of a microfarad. That's definitely very bad. Same thing over here on this section, and I'll move over to this one here. And same deal here. They all look pretty close. So that makes me wonder if the actual grounding has just come off from the can inside. Usually what they do is they take the common or the ground from all 3 capacitors, twist them together, and then attach one wire to the can. So let's just test between the actual capacitors themselves. And yeah, we have some capacitance there. Let's go over to this one here. Yeah, so it's obviously damaged inside. It looks like the negative has come off, the negative that attaches to the actual can, so it's either corroded off, or maybe at one time something shorted and it blew the common off inside. So definitely a damaged capacitor. So that's the reason we have so much hum here. So what I need to do is replace all 3 of these capacitors. Now the capacitor itself isn't leaking. It's absolutely fine just to leave this here. What I'll end up doing is I'll put in a terminal tie strip somewhere on here, and I'll put 3 modern capacitors in. By putting those 3 modern capacitors in and the terminal tie strip, will make it very easy to service down the road as well. Usually you just take the caps out if something ever fails, replace them, and you're off and running again. So that's what I'll do right now. I'll put a tie strip in here and get all the capacitors in, and we'll try it again. Actually, you know what we should do first is I'll give you an example of how the transformers are coupling on the upper chassis. That's just a bad design, right? So I'll give you an example. So the B plus is completely disconnected. So this just runs nowhere right now. This 220 ohm resistor is just completely open. So what I'll do is just fold this over here like this. And what I'll do is I'll get this attached to the isolation transformer and current limited supply. And what I'll do is I'll turn this thing on, and I'll bring this up to the microphone, and I'll let you hear how loud the hum is in the speaker. So I'll just get that all set up. The B plus is unhooked on the bottom side, and the two tubes are removed, so there's nothing in circuit to drive that audio transformer just below the speaker. So I'll turn on the isolation transformer and variac supply. So basically what that's going to do is that's just going to apply AC to this transformer and just light the filaments in this one tube that's left over here. So this is the indicator tube for the wattage section. So what I'll do is I'll turn this on and we'll take a listen to the speaker, and you'll see how badly this transformer is coupling with this other transformer here. So the speaker is off right now, so I'll bring this up to the microphone like so. Watch this. And that's just from these two transformers being too close to each other. So really the only way to fix that would be to remove that audio transformer below the speaker and place it on this side of the chassis. And that's going to be pretty tight like this. It'd probably have to be on an angle. If I put it this way, I might still get a bit of noise. It would probably be better than what it is right now. It's so close. Like, you can just see the clearance there. Like, it's almost touching. So, yeah, kind of a silly design. Chances are I'm just going to live with that bit of hum and just leave that alone, because it's quite a bit of work and reworking just to, knock out that little bit of hum there. And of course, at that point, I'm really changing the design quite a bit of this unit as well. I have 3 new capacitors installed in this signal tracer. So this capacitor, and this capacitor right here replace what's inside this can. So the first capacitor that was in line with the B plus here, so the very first filter, is 50 microfarad at 200 volts. That's what's inside this can. That's been replaced by 82 microfarad at 450 volts. So yes, this is an overrated component, and that's absolutely fine. The second capacitor is the same as the first one, 50 microfarad at 200 volts. This has been replaced with a 450 volt part at 47 microfarad. That's absolutely fine in this portion of the circuit. The third capacitor in here, which was a cathode bypass capacitor, is a 20 microfarad part at 25 volts. That's what's inside this can. That's been replaced with a 22 microfarad 35 volt part right here. So this little teeny capacitor here has more capacitance and better voltage ratings than what's inside that big can right there. You gotta like modern technology. You can put these things really close to the tube socket as well. I really like that. Really good temperature ratings on these capacitors and everything. Very high quality components. Again, when I do something, I don't want to repair it again. This thing is going to be on the old time workbench, and we're going to use this thing to troubleshoot other pieces of gear. So I want this thing, to stay together and be very, very dependable. So some very overrated components. The 68k ohm resistor that was tied to this capacitor here with the orange lead is now jumping over here. So I've installed a new 68k ohm resistor right here, and it joins to the same area, and that orange lead runs just right over here, a nice little short run to this capacitor. So this capacitor is replacing this one. As you can see, I've moved the resistor over and tied it to this point right here. So this is a ground, and this is a ground right here. So the B plus runs to this side of the cap, and then I've just bridged these two grounds to the chassis ground right here. And again, this is just a cathode bypass capacitor, so this is across this cathode resistor right here. And that's really all it takes to really calm this circuit down. So we're going to take a listen to the difference, and then I'm going to show you a real common mistake that a lot of techs make so that you don't make the same mistake. So I'll turn this thing on. Let's take a listen to it. Actually, there's a bunch of things I'll tell you about here that cause techs to so-called chase their tail in audio circuits. So I have the microphone really close to the chassis. I moved it really close so we could really hear this, so I don't really have to lift this thing up. That's the difference. Now, the little bit of hum that you hear there is a combination of that transformer coupling and basically open line hum, so you could call that signal path hum. It's listening to me sitting at the bench. That's where the hum's coming from. Watch what happens when I touch the chassis. Calms the hum right down. And that's because this is all unshielded right now, so this is just picking up all sorts of noise. When this is back in the metal case, none of this will be an issue because, it'll take care of all of that. It'll be completely shielded, aside from, the transformer coupling to the audio transformer. So quite a bit of difference there. Quite a bit quieter as well. So this is a real common mistake. A lot of audio guys will chase this hum around. They'll be like, where's that hum coming from? Where is it coming from? When a lot of the times it's coming from them sitting at the bench, or it's even coming from the line cord itself, just being too close to other components inside the amplifier chassis. And I'll talk a little bit more about that here in the future. If I add one capacitor from one side of the line cord to the chassis, it'll make this thing completely quiet as well right now. So kind of interesting. I'll touch on that a little bit more in the future when we're looking at audio amplifiers and things like that. So what I'll do is I'll shut this thing off right now, and I'll discharge the capacitors. So discharge these caps, make sure that they're completely drained off. And they are. This is the capacitor discharge device that I've designed, and it's up on Patreon as well. I use this all the time to safely discharge these caps, because you don't want to go poking your fingers in here with one of these things charged up, because you'll get a really nasty zap. So this is a common mistake that a lot of techs make. A lot of techs will go into a circuit like this, and they'll take a brand new capacitor and they'll parallel it with the old one just to see if that's where the hum is coming from. Well, you can't do that in a lot of cases, and it'll cause you to so-called chase your tail in a circuit like this, because you just won't find the hum if you do that. So what I'll do is I'm going to parallel in just 2 sections, not even 3. I'll just take 2 of those sections and I'll parallel them in, so the old capacitor into the new ones here, and watch what happens. So I'll just attach this here, and I will attach this here. So this capacitor here originally attached to this point, so I'll just attach it back to that point. And this capacitor originally attached to that orange wire, and that's this capacitor now, so I'll attach this to the exact same point again. So technically I've paralleled in the new capacitors to the old ones. Let's see what happens when I turn this on. I'll just shut that off, because that's nasty. That's the reason that you cannot parallel or use the old capacitor as tie points, even if the capacitor seems to be open. The old capacitor has to be completely disconnected from circuit. What I'll do is I'll just discharge these capacitors now. Keep an eye on these LEDs, see if there's any light here. Oh, there is a little bit. And this one here as well. There we go. So just get this out of circuit. So you can see the effect of paralleling these things up that can't be done. The reason that this is happening is, if you recall, when we looked at this earlier with that other capacitor tester, we could see that basically the negative or the common lead has been blown off, corroded off, or whatever. It's just disconnected inside the can. So these capacitors are connected together because all of those common leads are still connected together inside the can. That's why we can measure capacitance from one section to the next. So basically what I'm doing is I'm taking these capacitors here and I'm putting these 2 capacitors across this point here to this point here, and that's what's causing the hum. So I'm effectively bridging 2 capacitors in series inside this can over these 2 capacitors right here, from this point here to this point here, and that's what's causing that hum. And that's why you absolutely cannot use the old capacitor as a tie point. Very, very important thing to remember. And even if you're troubleshooting, you can't even bridge capacitors in, because you just wouldn't find the hum in this case. Well, now that we've gone this far with this little signal tracer, it'd be kind of a shame just to put it back together and leave the hum in there because of the transformer, the way it's put into the chassis and things like that. So, as I say, we've modified it to this point. Why don't we just keep on going and let's make this thing the best that we can make it. So what I'm going to do is remove this capacitor here. I'm going to take this transformer and move it over to this portion of the chassis so I can get it far away from the power transformer. You know what I'm going to do is I'll grab a small speaker and I'll take this audio transformer and I'll attach just the speaker leads to this external speaker, and I'll hold it up to the microphone and I'll move the transformer around the power transformer, and you'll see how badly they couple. So even though this thing is shielded, it's still going to couple to that transformer there. So let's get this thing out of the way, and then there's another silly thing that they've done that I'm going to address as well. We'll tackle one thing at a time here. I have both the audio transformer and the capacitor removed at this point. I've installed a rubber grommet here and I'm pretty much ready to install the transformer on this portion of the chassis. Here's a quick look at the faulty capacitor for those of you that are interested. So since I have the transformer removed, what I'm going to do is move it close to this transformer, and I'm going to hold this speaker up to the microphone here, and you can hear how badly this will couple with that transformer. So I'll just hold this up to the speaker like so. So you can see how important component placement on the upper portion of the chassis is, and that's so basic. I have no idea why they mounted all these transformers like this. So I say probably an inexperienced engineer or something put this thing together. So what I'm going to do is mount that transformer over here like this, and we'll see how much that knocks the hum down, and then we'll go on to the next thing that will be affecting the hum. The transformer is now installed, and that went pretty quick. So let's take a look at the bottom portion of the chassis here. So I installed a terminal tie strip here and just ran the wires up to their original area. On this portion of the chassis, what I did is I just soldered the common, let's get this into the focus here, common of the transformer to the chassis, because the speaker itself just grounds to the chassis, and then the green wire was the perfect length. It led right back up to that switch again. So that worked out very, very well. So I'll get this all positioned and plugged back in, and we'll see the difference in the hum. Okay, let's take a listen and see what a difference that made moving that transformer out of the way. So I'll click on the isolation transformer and variac apply right now. I don't know if you can hear the hum from just the transformer and the variac supply. You might be able to hear that as well. That made a huge difference. The reason I'm touching the chassis is because it's picking me up. That made a big, big difference. And there's still something else we can do as well. So that was definitely a worthwhile modification. So the next thing we're going to do is look into a hum balance control. Taking a look at this Stark Model ST-2 signal tracer schematic, they've done another very interesting thing in the filament circuit that we are going to correct. So normally in a balanced filament system, the center tap of the filament winding, which this does not have, would run to chassis ground. Or in a case like this, where you don't have a center tap on a winding, you run a separate hum balance control, which is just a VR across the winding, so from end to end on the winding, and then the wiper would run off to ground, and you adjust the VR for minimum hum. That's the proper way to do things. Well, what they've done here is they've used the highest gain stage vacuum tube, and they've taken the filament center tap, and they're running that to ground. So that's going to get corrected, and I'm going to put this VR into the chassis. This is a 2.5 k ohm VR, and I'm going to adjust this for minimum hum. So I'm going to put that somewhere on the chassis where I can very easily get to it. So right about here, there's a little open spot under here. So if I remove the back panel and I want to make a hum balance adjustment, I can just take the back panel off and get right there, put my screwdriver in and adjust it. I really don't want to be putting it anywhere over in here or somewhere where I can't get to it. And there is a little open area under here. So I'll get that hum balance control installed and I'll show you how that works, and we'll try and reduce the hum a little bit more. All right, let's adjust the hum balance control. So I'll turn the unit on. Let everything warm up. right about there is its quietest point. So it's working out very well. So now all I need to do is put the BNC jack in the front of this thing, change this capacitor right here, put another 0.2 microfarad capacitor in there, and I'm ready to try the thing out. The hum balance control VR is installed right here in the chassis, and that's at the back side of the chassis. You can see the twisted filament lines are running over here to the filament pins on this tube socket. Now you'll notice that these brown leads are a little bit smaller than the green leads here, and that's absolutely fine because these aren't really carrying any type of current. The wiper for the hum balance control runs all the way along here. You can see the black lead runs all the way over here up to the tube socket here to a low hum point on the chassis. Now when I say low hum point, finding the best spot on the chassis for a star ground is a little bit of a job in itself in any design, just because the chassis itself is carrying current through it. And if you bring the ground on certain points of the signal path to different parts of the chassis, you'll notice a hum. And then just say, all right, you had a wiper and you were dragging, say, an alligator clip or something along the chassis, you would hear the hum get lower and lower and lower as you get over here. And then as you pass this spot, the hum would start to pick up again, and it gets louder and louder and louder, and it's going to be louder by the transformer. And as you get over here, it would get pretty loud. So then as you drag the alligator clip back over here again along the chassis, you would find that the lowest hum point is at this point here. And that's a real trick in amplifier design. Whenever you're designing an amplifier, you want to find on the chassis where the best ground is. And that's why a lot of amplifiers have a star grounding system. That's quite a bit different than in an RF application, because in an RF application, having long lead length means inductance, and you cause lots of issues with long lead length. In audio application, that's absolutely fine to have that longer lead length because of the lower frequencies that the amplifier is dealing with. It's not dealing with higher frequencies. I'll talk a little bit more about this in the future in different types of designs, and this applies to everything. This applies to modern equipment. This applies to circuit boards. This applies to everything. Longer lead length means inductance, and when you're dealing with RF circuitry, that's your enemy. Again, since this is audio circuitry and the frequencies are much lower, you can get away with that. And there is a balance point too. So by having that longer inductance, or those longer lead lengths in an audio circuit, can actually be beneficial. Again, I'll talk more about that in another video. That's an entire topic within itself. So finding the correct grounding area. So anyways, this is a part of the chassis where the hum is very low, and this is far away from the transformer, and this is where that 12AX7 or that 7025 is mounted, right over here in this area. And that's the reason that I didn't just ground this over here. I ran the ground all the way over here, right to this area. So that's all done. I've installed the BNC connector on the front here. So I'll show you the front. And I've also put the speaker grill back in. That looks really nice. So there's the speaker grill. And that's got that hammer tone finish on it. It's kind of hard to tell the hammer tone because it's got so many holes in it and everything. But it's a really nice color. Almost like a really dark black, kind of like an ash, smoky gray kind of color. It turned out really, really nice. So the BNC's in here, everything's all ready to go, so I can put all my different probes on this. The face cleaned up really nice. There's still some scratches around the border, but that's where this actually meets the case itself. It has that curled edge on it, and it meets this. So all in all, there's a few scuffs on the face, but it's looking really, really nice. It cleaned up very well, the little knobs cleaned up and everything. So since I'm using stainless hardware, I also changed the screws on the face with some nice screws. The other screws were rusty, and looks like somebody had stripped them. They've been tightening things a little too tight, and they've kind of marred the screw. So I put all stainless screws in the face here, and they're all matching screws. So that worked out very nice as well. So this is cleaning up really, really nice. I really like the look of that grill. Much nicer than that horrible beige color. And the case is the same color as this. And you'll see that here in just a little bit. The case turned out just really, really nice. I'm very happy with the case. So all in all, it's coming together. The next thing that we really have to test on this is the watt meter section, and that has to do with the eye tube. So we want to make sure that this little area is working well. What this thing does is you plug an appliance or whatever in here, and you rotate this knob just until the shadow angle starts to open. So there's a little gap in the shadow angle, and then wherever it's pointing is how many watts it's drawing. So it's using, this is almost like a little CRT. These are known as eye tubes. So, and at any rate, we'll see how well that works. I'll plug different loads in here, and we'll turn this up, and we'll see how accurate the little watt meter is on the face. It's handy to find out if you're going to test an older radio or something like that. You know, you can't really bring it up slow on this. This is just kind of an all-out watt reading. So if you plug anything into this and it is pulling excessive wattage, you know, there's not really anything, unless you have a fusion line or something like that, that's going to, you know, deal with that, right? So this is where a dim bulb tester would really help. So something like this and a dim bulb tester combined would be a really good little design. An eye tube for a watt meter and a dim bulb tester, so if the bulbs light up really bright and, you know, you can tell that there is something wrong. Again, this thing, if you plug it in, you know, it's just going to show extremely high wattage if something is really wrong. And by that time, usually by the time that, you know, you've sensed all that kind of stuff, it's almost too late. But still handy. You know, there are applications where the watt meter is really nice. So we'll make sure that this portion of the circuit is working. Now everything is working, and the hum is about as low as it's going to get at this point with all of these modifications, unless of course I'm going to want to change this one capacitor and really up that capacitance. You'll recall when I looked at the design, I said, you know, this is, you know, it's kind of low, and there is no filtering on this side here. So, you know, it's going to drop the ripple, you know, down quite a bit by installing these new capacitors. Obviously, you heard the difference in the hum. It was pretty crazy. I'll talk a little bit more about that, and what I'm going to do is I'm going to show you some examples of the results now that these capacitors are changed and what you can expect. And I'll talk a little bit about what you can expect when servicing a half-wave rectification design, whether it be an All-American 5, All-American 6 radio, one of these devices, or something like this. So this is something to keep in mind, and this is something that really isn't talked about a whole lot. So you'll get some first-hand examples of exactly what to look for if you're dealing with a design like this, or, you know, as I say, an older radio or something like that. When the troubleshooting procedure began and this little signal tracer had a lot of hum, that led me to check the very first capacitor in the B+ line, and that was attached to this end of this resistor over here. So this resistor was bent over here and attached to one of the legs on this can here, as well as those red wires as well. Since I've installed newer capacitors, I've put a terminal tie strip over here, and I've installed the new capacitors like that, excluding the cathode bypass capacitor, which is attached directly to the cathode of the tube here, right on the tube socket. So all I've done now is I've taken this resistor and bent it over here to the new capacitor and attached everything over here on the terminal tie strip. So everything is as it was over here. It's just mounted in a different area with more modern capacitors. Now, if you recall, when we measured the ripple at this point, it was incredibly high. We had 9 volts AC or something up here. So let's compare the new capacitors to the faulty capacitor. Let's see how much ripple is at this point now with these new capacitors. And this capacitor here even has some more capacitance. The original was rated at 50 microfarad. This is now 82. So let's take a look. This thing is on and it's warmed up. What a difference. 9 volts down to 1.3. Now, some of you are saying that's still a lot. There's 1.2, 1.3 volts AC there, and look at that nice sawtooth-looking waveform on the scope there. Want to know what's even more interesting? Is this point here is what basically powers this tube right here. So this is attached to this tube through the audio transformer. Why is the hum so low? I'll answer that in a moment. You can think about that. Let's test the ripple at the second capacitor. And that's incredibly low. Why is the ripple lower at this capacitor than it is at this capacitor? Hint, what's between these two capacitors? This capacitor here is the filter for the preamplifier tube, so we would definitely need low ripple at that point. So since this is attached to the preamplifier tube and we need low ripple for the preamplifier tube, why is it okay to have 1.3 volts of ripple on the output tube? Again, I'll answer that in a moment. You can think about that and try and answer that. So now we have lots and lots of ripple on this very first capacitor. I'll try and throw you a couple of curveballs here and see if you can get the answers right. So what I'm going to do now is I'm going to shut this unit off, and I'm going to take a 47 microfarad capacitor, the same capacitor that's over here, and I'm going to put it in parallel with this one. So I'm just going to put it right across this one. What do you think is going to happen if I do that? What do you think is going to happen to that ripple? Make your guesses now. So what I'm going to do first is make sure that these capacitors are discharged very well. And they are discharged. Another question you may be asking yourself is, why are you continually going in there and discharging these capacitors or making sure that they're discharged when, you can't see any glowing of these LEDs? They always seem to be discharged when you go in there. Well, the answer in short is the tubes themselves are discharging these capacitors because of the thermal mass in the cathodes. These are indirectly heated vacuum tubes. They're not directly heated, so there's quite a bit of thermal mass in there. But you can never be too safe. You always want to make absolute sure. If there's ever a fault in the circuit, these capacitors could remain charged. So if you want me to get a little bit more into why these are discharging and what's happening with the thermal mass there, I'll quickly touch on that. So the heaters inside these vacuum tubes are inside of a cathode sleeve. So there's a filament like what you see in a light bulb, but it's tucked inside of a little pipe inside the vacuum tube. And that filament, when you turn the unit on, it applies heater voltage to that filament. The filaments inside start to glow really hot, and those filaments have to heat up that pipe. That pipe is the cathode, and it has a special coating on that cathode. And the cathode is what emits electrons inside the vacuum tube. So in order for the vacuum tube to work, that pipe has to glow orange so that electrons are, we have electron emission inside the vacuum tube, right? And that goes for both of these tubes here. Now, some tubes are directly heated and some tubes are indirectly heated. These tubes are indirectly heated, so it takes between 10 and 20 seconds for the filaments inside that pipe to heat that pipe up nice and orange. That's why when you turn on an old radio, it takes a while for the radio to come on, or if you have a vacuum tube amplifier, you turn on the vacuum tube amplifier and it takes a while for the sound to come out. It's because those pipes have to heat up. There's a little bit of thermal mass inside there. Well, the same thing happens when you cut the power to the power supply. So if I shut the AC line off, so I shut it off either here or by the switch, of course the whole power supply and everything is going to shut down, and the heaters inside the tube are going to shut off. So those filaments inside that cathode are going to get cold. Well, since there's so much thermal mass inside that tube, that cathode is still glowing orange, but it's slowly cooling off. Well, as it's slowly cooling off, because the power has been cut, the tube is still working. There's still electron emission happening. So what's going to happen? Since it has no power supply powering up these capacitors, what's going to happen to the caps? Well, these things are going to do the work now. What's going to happen is the tubes are going to use up the charge inside these capacitors, and it's going to drain those caps off really, really fast. So these things are kind of acting like batteries for a very short period of time when you cut the power. So what's happening really is the tubes are staying into emission longer than these things can supply a charge, so it drains these things right off. Here's the thing, if you had a very, very large capacitor in the power supply, the actual capacitor may supply enough current to those tubes as the cathode is slowly turning off to still end up with a lot of voltage. So you always have to make sure that the capacitors are discharged, or there could be, quite a bit of voltage lurking in the chassis. And in some cases that could be lethal, just depending on what type of a situation you're in and what kind of amplifier. Some of these big vacuum tube amplifiers have huge capacitors inside them, and you shut the amplifier off, it'll drain the capacitors so much, but there's still a little bit left. And then after that, we get into another subject, which is called dielectric absorption. It almost appears like the capacitors are charging themselves back up again, but they're not. Really what it is it's dielectric absorption, and I'll get into that in a future video. So it'll drain the caps off, and then there's no more emission in the amplifier. The caps are sitting there and it almost appears like they're charging up again. So I'll touch on that in the future. So what I'll do now is I'll grab that other capacitor. There's so many different things I could explain. I could make so many different videos on all of these topics and keep going and going and going here. So I will make a video on all this kind of stuff here in the future. It's just that if I keep talking about all of these small little aspects, we'll never get through this video. So 47 microfarad capacitor in parallel with this one here. So I'm taking this exact capacitor and putting it across this one here. So now we have a lot more microfarad. So we have 82 microfarad plus another 47 on top of that. And the boots are far enough down here that nothing is going to touch or short out. So now I'm going to turn this thing back on again. What do you think is going to happen to the ripple? Take your guesses now. Here we go. Turn it back on. And I have something that's going to throw you for a loop again here in just a moment. This will get a lot of the older techs. They'll probably be shaking their fists at me. So that should be kind of fun in a moment. Let's find out. So here we go. Now that I've got this cap installed, what do you think is going to happen? What are we going to see on the display? AC volts. Take your guesses now. Here we go. So it dropped it down to about 0.85. But as you can see, that's a nice looking little sawtooth on there. That's still pretty high. There's a lot of ripple at that point, still reading even 60 hertz right there. So it only dropped it down a little bit. So why is it so low at this capacitor, and yet it's so high at this capacitor? I'll answer that here in just a moment when we take a look at the schematic. So I'll just shut this thing off. I'm going to do one more thing that's going to really throw some of you for a loop. So I'll put this here. And I'll just make sure that this is all discharged. You might also be asking, what are you doing? Why are you doing this? Well, I'm scrubbing the leads. So if there's any flux or any kind of residue on the lead, I want to make sure that I've got a very good contact. So I scrub the leads. And that little kind of a little ridge that you see there, the focus is over here, that little ridge that you see in the probe right here helps with that as well. So basically what I do is when I go over to a lead on something, I scrub it like this just to make sure I've got a very good contact, because I want to make sure that these caps are very well discharged. I do that a lot when I'm testing for voltage as well. I'll scrub leads because sometimes you'll find flux or some residue will get under the probe and it doesn't make a good contact. So by scrubbing, you get a really good contact. So these caps are discharged. What's Paul going to do next? Well, let's take a look here. So here, we have another capacitor that we're going to put in line, and we're going to see what happens to the ripple if we install this capacitor right at the diode, okay? And I'm not going to be shy with the ratings either. So here we go. We have 200 volts, 200 volt rated cap. Same thing. Difference is, wow, 820 microfarad. We're approaching 1,000 microfarad here. I'm going to put this capacitor right at the output of the diode here, so right at this where it's basically coming into this resistor, I guess you could say. There was never any capacitor here, and that's not even on the schematic. So I'm going to put 820 microfarad right at the output of that diode. Now, some of the techs are probably going, "You can't do that. That's 820. It's going to cause damage." No, it's not. So here we go, put it right here. So it's right at the output of that diode. Why this capacitor will not cause damage to this power supply in any way, shape, or form, and this could actually be left in the chassis and it would work fine throughout its entire life. I'll explain all of this stuff here in some future videos. Again, I could just keep going and going and going about these little small details, and there's just so many things to cover. So a lot of the techs out there think that you can't go about doing this kind of stuff. What it's going to do is it's going to blow up the diode, or it's going to harm the transformer. The transformer won't be able to deal with this. I've heard it all. All of that is absolutely false in this case right here. It's absolutely fine. And I'll even be a little bit cheeky. And I'll show you something here in just a moment. Okay, so here we go. The capacitor is hooked up to the power supply. Power supply on. So everything's on, it's warming up. Now you're thinking, oh, that's got to be awfully hard on that diode or the power transformer, right? So what I'm going to do now is you'll be able to tell by looking at that little orange glow in the pipe there if you don't believe I'm doing this. So what I'm going to do is I'm going to shut the power supply on and off really, really fast. So if anything's going to happen, something is going to happen in this time, right? So here we go. I'm going to shut it off. You'll hear the switch clicking. Off, on, off. On and off a bazillion times really, really fast. It's off right now. On. And I'll do it again. So now, it's on again. Nothing's happened. Why is that? I'll explain that in a future video. Now, this wouldn't be so incredibly tolerant if this had a vacuum tube rectifier. This is a lot of capacitance, and vacuum tube rectifiers have a bonding wire that run from the cathode. So this is an indirectly heated tube, okay? So say we're talking about an All-American 5, so a 35W4 or something like that. And say there's a bonding wire from the cathode to one of the lead-out pins. Okay, so what happens is that bonding wire inside that tube acts as a fuse, and so does the filament itself, and that's why you see a lot of All-American 5 radios with no fuse. If anything goes wrong, it just blows that bonding wire off, and then of course the next weakest link is the filament itself. So there's almost really no need for a fuse in there unless you want to be very, very safe and add one. I still do. I still add fuses in there, but technically that's why you never found a fuse in those older radios. So there's your hint. The bonding wire in that tube is the weak point, and this thing right here would cause problems with that type of a vacuum tube, especially if you were to do what I just did. This is a diode in here, so there's absolutely no problem. So understanding why nothing happened to this is really just, it's a talk about the amount of current that the transformer itself can supply and the strength, the current rating of the diode and things like that. I'll get into all this stuff in the future. Again, I could go on and on and on. So here we go. Let's take a look at the ripple now at this point. So this is with a really nice filter capacitor right at the output of the rectifier. Okay, so here we go. Look at that, how low that is. What a difference. From almost a volt down into, we'll say, is hunting right now. It looks like about, we'll say 20 millivolts, something like that. Now let's go look at the second one here. So this is the one that's powering the preamp tube, or being the filter on the preamp tube, I should say. Look at how low it is over here. It's just hunting. So there you go, incredibly low with an added filter capacitor like this. Now, why in the day wouldn't they put something like this in the chassis? Well, A, cost. Back in the day when this thing was made, 820 microfarad at 200 volts would be a monster-sized can. And way back when, capacitors like this were very, very expensive. So to, purchase an 820 microfarad capacitor at 200 volts would be very cost prohibitive in a design like this. So what they did is they got creative, and they did this, and they used the same kind of topology in All-American 5 and All-American 6 radios. This topology here, excluding this large capacitor here. So the original topology, they used that in AA5 and AA6 radios, and they could get away with it. Why could they get away with it with so much ripple, and especially that ripple being tied directly into the audio output tube? Why could they get away with that? Well, what I'll do is I'll grab a schematic here and I'll explain a whole lot of things to you why all of this works. And it works not too bad. Of course, leaving this in here right now would knock the hum down. It would even take the hum down a little bit more, but at this point, it's so incredibly low that adding this capacitor into the circuit is only going to take it down just a little bit more than it already is. And at this point, it's a balance, right? At this point, it's a balance. If I wanted a very quiet circuit, this is a signal tracer. This thing isn't an audio amplifier. It's not a radio that's going to sit by the bedside and you're going to be listening to it late at night to your favorite radio show or whatever. It's a signal tracer. It sits on the bench. It usually sits a ways away from you, and it's used as a test tool. So that little bit of hum that you heard earlier before with these two capacitors is completely tolerable, especially now that we've done all of these other modifications, moved the audio transformer and added the hum balance. It's just so minimal. So I'll get the schematic and I'll start explaining all of this stuff. The modifications to the model ST-2 signal tracer are as follows. The filament center tap of the 12AX7 is now open. It no longer ties to chassis ground, so pin 9 is now floating. A variable resistor has been installed across the filament winding, and the wiper of that variable resistor now attaches to chassis ground. The rating of that variable resistor is 2.5 k ohms, so that gives us a hum balance control. T2 has now been relocated. Originally, T2 was too close to T1 and they were coupling, giving quite a bit of hum at the speaker. T2 has been relocated to where the original filter capacitor sat. The value of C8 has been changed to 82 microfarad. The value of C9 has been changed to 47 microfarad. And the value of C7 has been changed to 22 microfarad. A BNC connector or jack has been added to the face of the unit, so it's been modified so that I can use different probes with BNC connections. The line cord is still temporary. I haven't installed the line cord permanently at this point because I need to put the back on the unit, and the hole in the back panel was a little bit too small to fit the plug through. The 68K resistor has been replaced with another 68K resistor just because I had to relocate it, and the original resistor, the lead was too short because it was installed into a different area, so I just replaced the entire resistor. Other than that, components have been moved around a little bit, just moved around, and wires have been moved. Not much has been changed. Now, the watt meter section still hasn't been checked yet, so this entire circuit, we're going to do that here in just a little bit. We'll just get the amplification chain, basically the signal tracer, out of the way first. So if you recall, at this point here, we had 1.3 volts worth of ripple. Now, this point here, if we follow this path, runs down here into this switch. If we give this switch one click clockwise, pin 4 and 5 are going to connect to pin 7. Pin 7 is acting as a wiper, so when we click this one click, this larger area will contact this arrow. These two are ganged, so these two switches will do the same thing. When I say ganged, they have one common shaft in the switch. So now this is now connected to this point. So technically this point here is now connected to here. The B plus now goes through a 10k ohm resistor into this 47 microfarad capacitor, and up this path to the screen grid of the 12CA5 tube, and up this path here to the plates of the two sections of the 12AX7 here. If we also follow this path down here, we'll also see this point here is connected to this point here at this point, and it goes down here. Since we've clicked this one click clockwise, again, pin 4 and 5 will be connected to pin 7. So now this point is now connected to this point here. So we'll see a direct connection from this point with lots of ripple right directly into the audio transformer and to the plate of the 12CA5 tube. Now you're saying to yourself, that's a lot of ripple to be on here. How come this thing isn't humming a whole lot? Well, they've chosen the 12CA5 because of its power delivering capability. This is designed to drive an audio transformer. So there's not a whole lot of amplification happening here, so that little bit of ripple really isn't affecting this circuit. Remember, this transformer here is doing impedance conversion. A 12CA5 tube has a very high impedance, and we need to take that impedance and convert it or transform it to a lower impedance that will better match our speaker. And that's what the transformer does. We're just basically taking this high impedance and converting it into something that will drive a speaker. So not a whole lot of amplification here. Where it really matters is in the plate supply of these two tubes, but you'll see that the B plus goes through this 10K resistor here and gets filtered again by a 47 microfarad capacitor, and then of course that feeds the screen grid and the two plates of these tubes over here, right? You can see the path all the way up here to the two plates. Well, why is there less ripple at this point than there is at this point? Well, we have another capacitor here, and we also have a 10k ohm resistor in the path. So the strength of the ripple is greatly reduced at this point. So by putting another capacitor here, we can almost virtually eliminate it. And there's so little ripple at that point that it's not really affecting the amplification chain all that incredibly much. That's basically what's going on. So if we look at this circuit here, when I installed that really large capacitor, that 820 microfarad capacitor, I put that at this point here to ground. So basically right at the cathode of this diode here. So what's really happening? Well, we're adding a whole lot more filtering in at this point here. Now, if we get rid of the ripple, what's going to happen to the DC? the DC is going to shoot up. This is going to go up to about 160 volts or around that area. And we're going to have about 150 volts over here. Well, of course, it's going to up the voltage a whole lot to the circuit. Now, it's really not going to affect things too incredibly much other than take this out of its design parameters a little bit. But again, way back in the day, they didn't have capacitors like that available, so they made do with this particular circuit arrangement. And as you can see, it works very well. Still just a little bit of hum in there, but it's livable. It's not really worth adding that extra capacitor in there at this point. And that's really what's going on in this circuit. Now, if we take a look at paralleling the old capacitor, so the old one that was faulty, if we were going to parallel that into this circuit, why would putting these new capacitors in the circuit not affect this? Why would the hum still be there if that old capacitor was there? Well, this is the reason. If I take a pen, which I have over here, just about lost my pen and all the stuff on the desk. We have 3 capacitors in that old can technically, okay? So I'll just draw 3 capacitors quickly here. I won't draw them as being polarized capacitors, I'll just draw them as 3 capacitors. So this goes off to the can or to ground, and we have our 3 capacitors here. So now, since this is the can and this is tied to ground, we know that this is open. So this is blown open or rotted open inside there. So now we have 3 capacitors just attached together, and this is completely missing. So if this was the 50, this is the 50, and this here was the 20 microfarad capacitor. So since we have 2 50s, we had one here and one here, what's happening? Well, we have a path like this going through here. And also going through here, but we'll just ignore this for now to keep it simple. So we have basically 2 capacitors in series. So if we're to look at this, we would put a capacitor here and another capacitor here, and we could just take that and tie that to this point right here. Not joining these 2 lines here, but just attach it to this lead right here, okay? So we're now taking the ripple from this point and putting it through these 2 capacitors right here, completely bypassing this component right here. And we're taking all of that ripple that was originally there and putting it here. And that's the reason it made this entire circuit hum, because we have a path right through here like this. And that's why you can't parallel these old capacitors. So if something like this happens, you're kind of almost fooling yourself into continually searching for that hum, because you would put those new caps in there and the problem wouldn't get solved. So that's really what's happening. So if we wanted to really shorten this up, we could just really do this. That's really what's happening at this point. Completely bridging this out and taking the ripple from this point and putting it right here. So that's the reason the hum didn't disappear when we paralleled those capacitors originally. Okay, let's check to see if the watt meter works. I've got my light socket and a 40 watt light bulb. So I'll screw this in here. And now, just before I completely connect this here, what we want to do is move this just until the shadow angle just starts to open. When that shadow angle just starts to open, this should point to the appropriate wattage. So I'll give you an example here. So I'll just turn this on. There it is. Let's get that out of the way. So now what I want to do is I just want to rotate this until this opens. And you can see, it's starting to open about 30 to 35 watts. So it's a ways off. So I'll just remove this one here. Now, a 200 watt light bulb. I'll spare you from that on camera. I don't think I'll be holding this for too long either, so I'm gonna have to make this quick. It's a big bright light bulb. Okay, so here we go. And it's not too incredibly far off. This seems a little bit high. Just remove that. It's not too bad. Not too bad at all. It does seem like it's a little out, doesn't it? Let's go through and check. Just make sure that everything is okay in that circuit. Let's take a look at the way the wattmeter portion of this circuit works in this small signal tracer. It really is quite a simple little circuit, but it uses a very specific little component. It's quite simple as well. So I'll explain how it works on the schematic, and we'll take a look at some of the components in the unit just to make sure it is working okay, because it did look like it was off a little bit. So first of all, if we close switch 4 on the face of the unit, which is the main power switch, that closes this switch here, and it takes this portion of the line cord and puts it at this point of the winding of T3, and T3 is this little transformer here. So this end of the winding is placed in series with the load. So whatever we plug into the face of the unit, and that's this outlet right here, whatever we plug into that outlet is placed in series with this winding. So what does that tell us about T3? Well, T3 has a pretty large primary winding. It's a pretty special transformer, and there won't be many turns in that transformer as well. So what's going on? The more load that we place on this outlet or at this outlet here, the more load it puts across this transformer. The more we load the transformer, the more voltage is going to be present on the secondary. Now, you'll see that we have a 50k ohm potentiometer across here with the wiper that goes to a diode. So that 50k ohm potentiometer is on the face of the unit here, and they've written in calibrated steps in wattage all the way up to 500 watts, and it actually exceeds it if we go right to the end there, right? So chances are this transformer will deal with more than 500 watts. So what happens is, the more load that we place here, the more voltage we're going to get on this portion of the transformer. What's happening here is, you can see we have a diode with the cathode end that runs directly to the chassis. So that means that we have a negative supply right here. So it's creating a negative supply because we're feeding the positive right to the chassis, and we're running the negative off this way. We have a 0.2 microfarad capacitor, which is just acting as a little bit of filtering. And you can see we have a negative line that runs off here, and it goes through the switching, and it's going to end up at the grid of this 1629 I tube. What's going to happen is, the more load that we draw at that outlet, the higher the voltage is going to be. So it's going to be more negative. So when I say the higher the voltage, so if we start at 0, it'll be like -1, -2, -3. The more load we pull, it's going to go to -4, -5 in that direction. The higher the negative voltage on this line here, the more the shadow angle in this tube is going to deflect. So what that means is, the more load we pull here, the more that shadow angle is going to close. And then what we do is we calibrate this until we can open that shadow angle again, and when we get a little bit of a gap, we look where that needle is pointing on the face, or the pointer on the knob is pointing, and it should point roughly to how much wattage we're drawing at this outlet. And that's just how simple this circuit is. Nothing more than that. So what we want to do is we want to check the validity of a few components, and of course the major suspect here is going to be this 1N34A diode. So let's check that out first. So what I'll do is I'll move the I tube out of the way. It's just clipped in here like this. There is no power or anything connected to the unit at this time. You can just take this out and lean this down here, and we can get right to the VR. And as we can see, that little diode is right on the VR. So what I'll do is I'll go get some test equipment, get it placed on the bench here, and we'll check some components. The first component that I'm going to check is the diode, and I'm going to check these components in circuit using a curve tracer. One end of the diode is attached directly to the chassis, and the other end of the diode is attached to the wiper. So what I'll do is I'll just get the focus on there so you can see that a little clearer. So you can see one end of the diode is attached right here, and the other end to the wiper. So what I want to do is I want to make sure that the VR is roughly centered before I make any tests. So I'll take the common lead of the curve tracer and put it to the chassis, and I'll take the signal lead and put the signal lead right to the wiper. So the black lead is a common lead here, and then what I'll do is I'll just move the focus over to the curve tracer, and we'll take a look, see if this looks like a diode. And that does not look like a diode. That looks like a resistor, really low value resistor. So chances are we already have a problem here. So earlier on, Let's move the focus back over here again. Earlier on, I replaced the capacitor that was right here. It was a ceramic tubular style capacitor, most likely paper and foil inside, and a bunch of epoxy on each end. So I replaced that just to be safe. So I'll test this capacitor and just make sure that it's okay. So if the capacitor is okay, I should get what looks like a circle on the curve tracer screen. So I'll just move the focus back over to the curve tracer. And here we go. And that capacitor is fine. So now if I want to check to make sure that this VR is working okay, so it's working through its travel. Now we looked at the eye-tube earlier and we saw that the eye-tube moved open and closed pretty easily. Nice and smooth, I guess you should say, so most likely the VR is okay. But I'll show you what it looks like on the curve tracer. So I'll go from one end to the center here. So I'll move the focus back onto the curve tracer. So I'll go from this end here to the center of the VR and I'll rotate this. So as I rotate this, you'll see how the trace is twisting and it'll go right up to the top, and that's a short circuit. Now you'll notice how it kind of popped into place. So I'll just rotate this VR on the front of the unit here very slowly, and you'll see that nothing seems to happen. It remains like a dead short for a short period, and then all of a sudden, boom, it just pops into resistance at a very small spot. That's very common for a lot of VRs. So if you ever see that when you're using your curve tracer, don't worry about that. And as you can see, it moves smoothly throughout its travel. There is no problems with this VR. And of course, we verified that by looking at the actual eye tube on the face. As I rotate the VR, you could see that the eye tube is slowly closing and opening. So no problems there. So far, it looks like this diode is toast. So what I'm going to do is desolder one end of this diode. In fact, I might be able to just do that right now. Let's see if I can just lift one end of this thing here. I can. That's nice. It wasn't wire wrapped. Okay. Or they didn't curl the lead under. I'm thinking to myself, oh, this is not going to turn out good. But that was actually pretty smooth. It's surprising. Sometimes things go like that. So let's take a look at the diode again. So the wiper end is open. So I'll just... yeah, that diode's looking pretty ugly. This diode has changed its form to a resistor. It's changed its state. It no longer wants to be a diode anymore. It wants to be a resistor. This diode has resistor envy. So I'm going to remove this diode here, and I'll show you what a proper diode looks like. So I'll just get that underway, and I'll be right back. Let's take a look at the original diode, the diode out of the wattmeter on the curve tracer. So this is the little one right here. So what you see here is I've got the curve tracer attached to my digital voltmeter. So when I designed the circuit board inside this curve tracer, I also gave it a sleep circuit, as you can see. When I designed the circuit board inside this curve tracer, I wanted to give it the option of having an external digital display to take a look at the forward of diodes, the reverse of diodes, Zener diodes, and check out transistors and all sorts of things like that. So that's all built into this. You basically just attach this to any old digital voltmeter, anything you have, and it gives this old oscilloscope, which is now converted into a curve tracer, a digital display. So it's kind of handy. So at any rate, we can look at the forward of the diodes here. And if we were looking at a Zener, we could look at both the forward and the reverse. So I'll attach this into here and it'll wake up. So there we go. And as you can see, the original diode is looking pretty nasty. Right? Just a diagonal line indicating resistance. If it was a dead short, it would be straight up and down, so it's slightly resistive. So the 1N34A is a germanium diode, and I've got lots of glass diodes, tons and tons of glass diodes you can see here, of all sorts of different makes and sizes and shapes. This one here is really high quality. It's got gold leads on it. And this is another one that I picked out of my junk bin. So if I test this one here with the gold leads first, so I'll put this on the scope here. So on the curve tracer, we can see that this is the forward here. So if I turn the voltage down, you can keep an eye on this here. We should take the corner at around 0.6 of a volt. So you can see we're at 0.5 of a volt. And it'll start to take the corner right there. You can see how it's just starting to take that corner. So that's the forward of this diode right now, about 0.6. So I know that this is just a standard silicon diode. So germanium diodes have a really low forward of around about 0.2 or 0.3 of a volt. So I had to go through my junk bin, and I found another glass diode with long leads on it like this. They're not gold, but that's okay. So you can put this in the thing any which way you want. And as you can see, I'm at 0.6 of a volt, but I'm well into the turn. So if I back this off and bring that right down to where it just about starts making the turn, you can see it's making the turn about 2.24 of a volt. So you can see that this is definitely a germanium diode right down there, right? See, it's making the turn there. And it's well into the turn, about 0.3. So you can see definitely germanium. So this is what I want to replace this nicely shorted device with. Now, the specs of this diode aren't really too incredibly important as long as it is a germanium diode. Reason being is the voltage on this side is so incredibly low. You only need maybe -5, -6 volts, something like that. So you can see here, watt meter, -5.6 volts at 0 degree shadow angle, right? So we're dealing with really low voltage on this side. So pretty much any germanium diode is going to be just fine to replace this 1N34A. And that's what we have right here. So you can see it's coming into the turn at, 0.24. It's really low. It's well into the turn at 0.6 of a volt. You can see that. So definitely germanium. This is going to go into this circuit. I'll get that installed and we'll check the watt meter again. New diode installed. Let's take a look at what the 40 watt light bulb does. So here we go. Okay. Just till it opens. Right there. Look at that. That's what I want to see. 40 watt bulb. Okay, let's try that 200 watt bulb, see what we get. The incredibly hot light bulb. Whoa, that's bright. Okay, so here we go. Pointing right at 200. It works great. Here's an example of how the paint turned out. Pardon the fingerprints here and there from me holding it. That finish turned out really, really nice. I really like that hammer tone finish. You can see the case here. So that's sure going to look a lot nicer than that ugly beige color that it was issued in. So I'm looking forward to getting this thing all back together and seeing how it looks all assembled. So the next step for me is to get the line cord into the unit with the back of the case on. And I should be ready to assemble this thing. I'm not going to put the handle back on. I don't like the handle. I'll probably just put some screws in here to fill these holes so that it looks like something's happening here. But I really don't like those handles. And that allows me to put other pieces of equipment on top of this as well when this is on the old-time workbench. So I'll get this all assembled and we'll try it out. The signal tracer is reassembled and I think it looks absolutely great in that case. The color of the case and the grill really sets off the face, and even the colors of the binding posts, it just looks so good. I don't know why they didn't issue these things in a darker color like this instead of that horrible beige color they put on these things. At any rate, it works incredibly well. I'll give you an example. So the gain is right off. So it's right at the stop. I'll just put a standard cable on here. That's with the gain off. I'll give it just a little bit of gain. That's just a bit of gain. That's picking me up. So if I touch the case, it gets quiet. This is shielded right up to this point and it's still hearing me. So you know what's going to happen if I touch this, right? It's just going to get incredibly loud. Whoa. Whoa. I couldn't even imagine if I had this pointing at 12 o'clock, it would probably destroy the speaker. Incredibly sensitive unit. So this will be great for signal tracing. I'll put on an RF probe that I have, which is right here. It's a very sensitive RF probe I designed some time back, highly sensitive. So this is for sniffing noise, crackly components and things in circuit. So I'll just turn this up. So it's just picking up switch mode noise right now. So I'll bring this close to the microphone. That noise is the camera. So that's a switch mode or a bunch of stuff going on inside the camera. Maybe the switch mode supply that's powering it. Let's bring it close to another one. And it's another lamp. Wow, incredibly sensitive. I don't know what else I have here that makes noise. Anyways, RF probe, very sensitive. You can see if I'm holding the ground of the RF probe just to keep it quiet, but if I shield it with my hand, it's just picking up random switch mode noise. Gets louder when I open this towards the microphone and the camera. So very, very sensitive. The gain is hardly even just moved there. Look at that. So the noise works well. There's a little bit of a thing that you need to know about the noise circuit. Whenever you click these things onto noise, it puts about 100 and some odd volts on the probe. So if you don't know that, don't use the noise section in one of these noise tracers. And definitely, or signal tracers, you got to be very, very careful with that because you can get a pretty decent zap. Now, there's a high value resistor in line with this so that you can listen to noisy components. And I just happen to have one. I saved one here. I'll just reach over here and grab it. And I'll do a comparison for you. So there's two resistors here, high quality Allen Bradley style, and 2% tolerance. And then there's an old roundy here. So I'll let you take a listen to both of these things. So it's not on noise. You can see that I have it on trace only. You need to remember this with these signal tracers, or you'll buzz yourself. So this is just a newer style Allen Bradley resistor, very good resistor. So I'll turn the gain right down. That's me. So I'm going to hold the negative here just so it keeps me quiet. I'm not touching that portion of the probe because that's live right now. And you can hear that's pretty quiet. Very quiet. Look at how much gain I'm giving this thing. So I'll turn this back down. I'll turn it back to trace because I don't want to touch this. So and I'll put this resistor in, and this one's like the ocean. So let's take a listen to this one. Put this back on noise. Listen to that. You can use this thing as a static generator. So just think if that was in an audio circuit. Very, very noisy component. Quite the difference. So the noise circuit works very well. And the nice thing about the wattmeter circuit on this is when you click it into wattmeter, this gets nice and bright. See that? And it makes everything go quiet. Switches a bunch of things out of circuit inside. And, I'm ready to use the wattmeter, and I demonstrated that earlier. That works just perfect. Very, very well. So all in all, I'm extremely happy with this, and I'm glad to add this to the old-time workbench. It is coming together, and the Vitalizer is getting close to completion. That is such an incredible project that I'm putting smaller projects in the middle so that I can, get some videos up for you guys. And of course, it gives me a break from that thing because that thing has just been all-consuming. So, yeah, that's been quite the project. But this one is done, and it looks fantastic and works fantastic. And I'm looking forward to using this with you guys and showing you how to troubleshoot circuits with this signal tracer. Very, very happy with the results. I'll share some vacuum tube knowledge with you that not a whole lot of people know. I'll start with the filament system here. So we noticed in the signal tracer that the filament lines were twisted together like this and pressed close to the chassis. And the reason that's done is to stop the filament system from interfering with other parts of the circuitry to keep the hum down. This is pretty common. A lot of people do this, and this is pretty well known. So usually this is part of a balanced AC filament system, a transformer with a center tap running to the chassis, or just a hum balance control. So the filament lines have to go up to a vacuum tube to light the filaments. So if we take a look at a really high quality vacuum tube and we look at the filaments inside, so this is a really sought after vacuum tube. You can even see the little Telefunken diamond on the bottom there. So if we look at the filaments inside, you can see those little white wires. They run up inside a cathode sleeve, turn around and come back out again. And it's the same on the other side because there's two triodes in here. You can see the little filaments in there running up into the cathode sleeve and then coming back out again. So again, a very high quality tube. So if we want to take that to the next level, go to something with extreme quality, we can go to this 5751 5-star vacuum tube made by General Electric. Doesn't get a whole lot better than this. So you can see the filaments here. They run up inside the cathode sleeve and come back down. Same with this one, runs inside the cathode sleeve right up to the top and then comes back down again. Right, again, two triodes. Now, when we talk about high quality tubes suited for audio, we look at a 12AX7. Everybody knows what the 12AX7 is. But there's the 7025 version. You can see that 7025A. What's the difference in this vacuum tube? Take a look at the filament inside that vacuum tube. What's happening with that filament in there? Notice on that side right there? What have they done with the filament? That's how you spot a very high quality audio tube. And if you're ever building an audio amplifier, you want to look for the filaments that do that inside. Top quality tube right here, 5691. Look at the filaments inside that tube. Another really good audio tube designed specifically for audio. You can see the cathode right in the center of that tube. Right there. Look what they've done. And that's the difference between a high quality audio tube and just a high quality tube. So whenever you're designing an audio amplifier, and whenever you're wanting to search out some really good quality tubes, those are the things you want to look for. You want to look for those twisted filaments for the lowest hum possible. I'll talk more about this in a future video, and we'll actually do some experimentations with hum and all sorts of things. So there you go. Some vacuum tube knowledge that isn't normally talked about or discussed. Thanks for stopping by the lab today. I hope you're enjoying me sharing this information with you and the repair of this ST-2 signal tracer. If you are enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos coming in the near future. We'll be taking a look at vacuum tube and solid state equipment alike. So there will be a lot of troubleshooting, repairs, restorations, and even some circuitry design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way, you're going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video description. So just below the video description is a Show More tab written in capitals. If you click on that, it will expose the link. You can click on the link and it'll take you right to Patreon. I'm also sharing many of my designs and inventions up there as well. So there's a lot of custom pieces of test gear that you just won't find anywhere else. Lots of really neat things going on Patreon. All right, until next time, Take care. Bye for now.